Welcome back to Maths in an Empty Classroom with me, Mr. Southern. This is part 5 of the lesson on implicit differentiation, and in this video I'm just going to be looking at a final example that has an index variable. So what do I mean by an index variable? Well, an index variable, I mean that the power is a variable x. So here we have 2 to the power of x. So rather than y squared, where the power is a constant, 2 to the power of x, the index, the power, is variable. So that's what we mean with that. Now, before I actually go through this question, I'm just going to look very quickly at how to differentiate expressions of this form, because sometimes you're asked to demonstrate where it comes from, but after that you can just use the general result, which we're just going to derive here. So y equals 2 to the power of x. The first thing that we want to do to show how you would differentiate this is to ln both sides of the equation. So natural logarithm. So I'm going to say that ln y equals ln of 2 to the power of x. And the reason for doing that is what that means with my index rules for logarithms. I can bring this x down and I can say that ln y is equal to x ln 2. Now if I differentiate both sides of this with respect to x, ln y is going to differentiate to 1 over y, dy dx, because you're differentiating a y term in terms of x. Now x ln 2 is just going to differentiate to ln 2, because ln 2 is a number and it's the coefficient of x. So if I differentiate x ln 2, it's simply going to be the number ln 2. I'm looking for an expression for dy dx, so I'm going to write that dy dx equals y ln 2 multiplying up by the y. And then I'm going to use the fact that my original statement was that y equals 2 to the x, so I'm just going to substitute that back into my result here to say that dy dx equals 2 to the x ln 2. And this is a demonstration of how that works. After this, it is perfectly acceptable to use the general result, which is if y equals a to the power of x, then dy dx would equal a to the power of x ln a, where a is a constant, a is a number. So in this case, a is 2, we differentiate 2 to the x, we get 2 to the x ln 2. Okay, so let's now apply that to the question we've been given, which is we're given a curve C has equation 2 to the x plus y squared equals 2xy, and we're asked for the exact value of dy dx at the point 3, 2. So let's just write that original equation out then. 2 to the power of x plus, was it y squared? It was y squared equals 2xy. I'm just going to differentiate each term at a time. We now know that 2 to the x differentiates to 2 to the x ln 2. Y squared is going to differentiate to 2y dy dx. And on the right hand side we've got the product rule again. I'm not going to go through the whole thing again, we've done it in the 3 previous videos. So I'm just going to write that we get 2y plus 2x dy dx when you differentiate the right hand side using the product rule. Right, so I'm going to find an expression for dy dx, so I'm going to keep the 2y dy dx on the left and move the 2x dy dx over, and then that is going to equal 2y minus 2 to the x ln 2. Factorise out the dy dx on the left hand side, I should say. So dy dx 2y minus 2x equals 2y minus 2 to the x ln 2. And then dividing, we get that dy dx equals 2y minus 2 to the x ln 2. All over 2y minus 2x. Now crucially, you cannot simplify that expression because you cannot cancel that 2 because it's the power of x. You cannot cancel down that 2 because it is being ln'd, it's being put into the ln function. So that is the simplest form of dy dx. And what we've been asked for is the exact value of dy dx at the point 3, 2. So what I'm going to do now is I'm going to substitute in x equals 3 and y equals 2 to this expression for dy dx. So dy dx is going to equal 2 lots of 2 minus 2 cubed ln 2. That's all going to be over 2 lots of 4 minus, oh no, hang on, 2 lots of 2. Get ahead of yourself, son. 2 lots of 2, which obviously is 4, minus 2 lots of 3. So that is going to give us 4 minus 8 ln 2, all over 4 takes 6, which is negative 2. So that's going to simplify to 4 ln 2, dividing the negative 8 by the negative 2, minus 2 for dy dx. And that is the value of the gradient of that curve at the point 3, 2. And because I've been asked for the exact value of the gradient, I'm not going to work it out as a decimal, I'm just going to leave it in terms of ln 2, because that is the exact value that we've been asked for there. So there we go, implicit differentiation. Job done.